I believe I owe you all an apology in the stupidity of Friday with me being unable to connect. I actually forgot to hit record. So that the notes are up, but there's no recording from Friday because I was dumb. But I do have this set up. It is recording. I did just push the button. Little red light. We're good. So, conic sections. You should have seen this in your trig class way long ago, your pre-calculus class. Most of what we know about conic sections comes from a Greek text by an author by the name of Apollonius, who described these items geometrically. And he said, if you take a cone, I will imagine this triangle to be the side view of a cone, and you cut it with a plane at different angles, you get different shapes. If the cut you make is parallel exactly to the side of this, then you will come into the curve and never exit. You'll never leave the cone because you're going exactly parallel, so this line stays exactly the same angle as the side all the way down. And that means that the shape continues to grow out and down, or up and down, depending on which part of the cone you're looking at. Because technically we're looking at a cone not just as the bottom with the point at the top, but also this way. We're looking at both halves. And this is geometrically our definition of a parabola. If you cut at an angle shallower than the side, you get an ellipse because you come in on one side and out on the other, so you get an oval shape. If you cut exactly perpendicular to the central axis, then your ellipse is uniform in size, and that's a circle. If you cut at any angle steeper than the angle of the side of the cone, all the way up to vertical, you actually get a two-piece curve. You have a piece here on the bottom, you have another piece up here on the top, and that is a hyperbola. Now, by default, we draw our hyperbola cuts vertically. On page 674, we actually show all three of these through our double cone. The parabolas matching the side exactly, so we're only ever going to intersect the bottom nap piece of the cone. The ellipse goes in and out. The hyperbola has a piece on the top and a piece on the bottom. If you cut at any angle less than vertical, you'll get an asymmetric hyperbola. One side will be smaller than the other. But by a change of coordinates, you can actually rearrange this so it is symmetric by moving the center towards the side that is small. But because Apollonius was a Greek mathematician, he did all of this geometrically. And he did it in terms of distances. And so the definitions turn out to be determined by points and lines. So the definition, according to Apollonius, of a parabola is the set of points that are equidistant from some fixed point, which he called the focus, and a line called the directrix. I am personally amused. The trix ending in Greek is feminine. The directrix is the line which gives us direction, and it's female. Remember that. Women give you direction. It's important. So I can take this definition. I say, okay, I've got some point and some line, and I want the set of points that are the same distance apart for each of those two things. And what I can do is I can say, all right, well, I know at least one point has got to be in there. If I draw a straight perpendicular from F to that line, then halfway, that should be one of the points. So I'm going to draw this at a right angle and right here in the middle so that this distance matches this distance exactly. That's the point I'm going to call V for vertex. Now, every other point on this curve has to satisfy this same distance property. So if I move to the left a bit, I'm going to be a bit further away from F, aren't I? If I'm over here somewhere, I'm further than this point from F. So as I move over, I've got to move away from the line. This distance has to match that distance. If I move way over, I'm going to have to move way up so that this distance matches this distance. Now I've drawn this very poorly. This should be higher still, right? Because I need that to match this. That point should be way up here, shouldn't it? I've drawn this very badly. I want these distances to match. And now we see where we get our parabolic shape from. This is all well and good, but this is not a geometry class. I don't want us to do this geometrically. I want us to think in algebra and calculus terms. And that means using the distance formula. Let me make my life easy to start with. I'm going to take that picture and move it so that the vertex is at the origin, and so that D is some horizontal line. And that means that F is going to be some point on the y-axis. Do you want to put our point above the vertex as we've drawn it already, or below the vertex? We could do either. Doesn't matter. For now, I'm going to make P positive. I've added a piece of information. I've given you a distance. From this, you should be able to give me the equation of the line D. Say again? It should be. And since it's a horizontal line, equations for horizontal lines are y value, right? Y equals minus B. By the way, that's still true even if P is negative. Just turn those two into switch places, right? The dot would be on the bottom, the line would be on the top, but the value for Y would be the opposite of the one at the bottom. That's fabulous. With a bit of algebra, using the distance formula, I can show you that the equation for this parabola looks like that. Now, normally we write our equations as y equals, right? So it would be y equals 1 over 4p x squared. But the other version where there's no division is a little more preferable. P here, again, that's this distance, right? That's our distance P. That's the distance from the vertex to the focus. Yeah, I wonder what we'll call that. Do we take optics yet? In physics? A focal distance. And to that end, the line through that point, the sideways line through the focus, is referred to as the latus rectum, the side length. And its distance is exactly 4p. The distance from this side to this side is this number 4p. And that's called the focal diameter. In camera terms, that's called the aperture. Wait a minute. Yes, ma'am.
So all of this will always be true, or is it just true for
It's true all the time. Every single time. Whether it opens up or down or left or right. But if I want it to open left or right, I have to change this picture around. What do I have to do to my equation to make it go to the right instead of going up?
You have to maybe add x next to the number x plus 3 to change it to the right.
That would move it, but it wouldn't turn it. You're correct if I move the x's somehow, but that would still open this direction. If I switch the x and the y, that changes the orientation of my picture. Now, hang on a second. Notice that the coordinate for the focus changes because the coordinate's on the x-axis instead of the y-axis. That also means that the equation for D changes. Because now that is a different kind of line. What kind of line is D now? Say it louder. Vertical. And the equation for a vertical line is x equals a number. But again, I have that same focal diameter location. I have the same aperture, the same distance for the latus rectum. Now, most of those are geometric pieces, and we're not often going to use that except in application pieces, where somebody would ask, what's the focal diameter? What's the distance from the focus to the vertex? $64,000 question. Why would I give a flying about that distance? Do you know that you have not one, but two parabolas, either in your bag, in your pocket, or on the table in front of you?
I was thinking about that y was like both here on the y-axis instead of the x-axis.
Yes, but I haven't rotated anything yet. Where are the parabolas in your pocket? Right here. It turns out that a parabola has a wonderful property. If you put a light at the focus, it shines rays out that are perfectly parallel to the parabolic. They go exactly along that central axis. Every single parabola has this property. Anything that comes in bounces off the parabola to land on the focus, and anything at the focus can be used as an emitter. A microphone put here picks up any sound reflected off this parabola, a parabolic microphone, like you see on the sidelines of the football game. You put a light here, you get a spotlight, searchlight. So you have one literally sitting in your pocket. I want to build a satellite dish, it's going to be this shape. I want to build a microphone, it's going to be this shape. I want to build a reflector that directs light to your eye from a particular image, you know, like a microscope. %of the time, I am concerned with getting equations from information about my parabola. I'm getting the information of the parabola from the equations. Now, Leo, you said something very important. You said I could move it, right? You said I adjust the x and I adjust the y. If I move to the left or the right, we adjust x. We did this back in algebra class. If I write this, I've taken my entire graph and shifted it 2 units right. If I do this, then I've shifted it 2 units up. As a matter of fact, that's true in general. If you take your x and replace it with x minus h, you move h units horizontally. If you replace y by y minus k, you move k units vertically. Now, what's important to note here is that what you are seeing is that the number is subtracted. So something like this. If it was just y equals x squared, it would go through the origin. Because we've seen that graph 1,000 times. But now I've written y plus 1. Where is that moved to? Leo.
Would be down one because the opposite side would be the opposite there.
So it is moved down 1. My new vertex is at 0, -1. A question for you. Where's the focus? Where's the directrix? Answer both of those. I need one number. I need P.
The equation for px is y squared solved for p.
That's my standard equation, isn't it? 4py equals x squared, only we have the shift, so it's y plus 1 there instead of y. Wait a minute. If I match that up, what's the value of 4p? Leo?
Would it be 0 because -1 plus 1, that means
It's multiplied up there. What's multiplied in front of this y plus 1 in this equation?
4p.
That's what's down here. What's up here?
1.
1. Notice that is a positive value. That means that the focus is above the vertex and the directrix is below the vertex. And my graph goes around the focus away from the directrix. So my directrix is down here and my focus is up here. But now I can give you exactly those points. The distance from the vertex to the focus is this much. So the focus adds p. And the directrix subtracts. It's a horizontal line, so it's y equals minus 5/4. Now I know pre-calc was a long time ago. And this is obviously fresh in your memory. And you've seen a lot of it, right? I have a handout on Canvas. 2 versions. I have a PDF version. And I have a Word document version. They both say the same thing. I don't care which one you like. Download one of these. Print it out. Keep it with you while you are working on these exercises. But notice these are the standard forms. Now this one calls it A instead of P. So does this one, because I wrote these based on my trig book, not my calc book. But those handouts are for working with at home. They're not with you on the exam. So what do you do then? Run screaming for the hills. Not a bad idea. You ready for the best part? There's a bunch of applications already built into the calculator, right? Apps. What's number 4 say? Number 4. There's an option for a parabola. And if I go and I hit option 4, it gives me the standard equations. I don't have to have this crap memorized. It's right there. Apps. Yes, you must be in regular function mode. Get out of polar. But there you go. And what's more, you can give it the information. If you know H, you know K, you know P, you can actually put it in and it will draw this for you. Now, this must be the last one I did, so I'm not going to use this one. H was 0, K was -1, and P was 0.25, right? And if I hit the graph button, it draws that sucker for me. And it goes through 0, -1. I don't remember what my window is from previous settings, but I could hit zoom standard and it will go back to that. And then I can go in and ask it to graph. Oh, it actually fits the window. I'm terribly sorry. It automatically changed the window to fit this.
Which option? Maybe any other one.
I can't tell what your options are, but I only see 2 options on mine. Apps, conics, parabola, . And it depends on which one is squared as to which one you're doing, right? So I'm looking at y minus k squared or x minus h squared. But I actually just have this in front of me to remember the formulas, because that way I don't have to have them memorized. If you've got more specific calculator questions, please make sure you're in regular function mode. If you're in parametric mode or if you're in polar mode, you'll get weirder things. We'll look at those later. Make sure you're in regular mode, functions. Sure. If I do this first one, all right, I was actually asked in the next question I have sitting in front of me, what if my vertex is minus 4, 0, and my directrix is x equals minus 2. Now this is going to give me a different problem altogether, but let's see if we can figure this out. So if I'm at negative 4, 0, that's over there somewhere, right? And if my directrix is x equals negative 2, what kind of a line is that? What kind of a line is x equals 2?
Oh, it's
They're all straight. Horizontal, vertical, diagonal, what kind of a line is that? Vertical line, right? X equals is a number, and negative 2, by the way, is further to the right of negative 4. So that means that my focus is over here somewhere, and my parabola should go that way. Yes? Okay. With that in mind, what numbers can I get that I need for my equation? I need h, k, and p. Where do h and k come from? Yes, but from which point? And x goes with h and y goes with k. You can remember this in two different ways. H is a horizontal motion, or you can remember the dirty joke that k always goes with y. And if you don't understand why that's a dirty joke, remember the other one. P. How do I get P? What is P? That's okay. Terminology is not fresh. That's all right. It's, go ahead.
sorry, it's the y. Yeah, it's the like y cutting the y-axis.
That would be true if we were going through the origin. But now I'm not. I moved over. P is a distance. It's the distance between two things. What two things? Yes, it's the distance from V to F. It's also the distance from two other things. The same distance from V to D. How far is that? Aha! But we're going left, so I want to make it negative. Now I have all the information. Let's see how good my picture is. I will go back here, and I will say I want to enter a parabola that goes sideways. The one that went vertically had the x squared. So the one that goes sideways has the y squared. It even shows me that in the picture. So I hit enter there. H is negative 4, k is 0, p is negative 2. Enter. Hit the graph button. Trace negative 4, 0. There's my parabola. And it's going to the left, just like I wanted. which means you can give me the equation. You can give me the equation from this information. Because we know the equation goes y minus k squared equals 4p x minus h. So now I know the equation for this. Y squared equals minus 8 times the quantity x plus 4. Better, Jack? One of the options on that app is circles. But I'm hoping you remember the equation for a circle. The equation for a circle looks like that, where the center of my circle is hk and the radius of my circle is r. Now, a circle is a special subset of ellipses. Remember, we form an ellipse as long as we cut at an angle shallower than the angle of the side. Well, cutting horizontally is definitely shallower. So a circle is a subtype of an ellipse. It's often called a degenerate ellipse. So I'm going to change the equation here. I'm going to rewrite this equation to have a 1 on the right side. That's still a circle. It's just a slightly different form for a circle. But when I think of an ellipse and its difference with a circle, the circle is uniform in every direction. The ellipse isn't. Longer one direction than the other. How can I adjust this to make up the fact that I want x to be different in distortion from y? I can change the numbers. At the moment, these two numbers underneath the x and the y, they're the same. And that represents the fact that the radius of the circle is the same to the left and right as it is up and down. But in an ellipse, we have a longer side and a shorter side. So I'm going to name those. In an ellipse, my center is still hk, but I have a long direction and a short direction. The long direction will be A, the short direction will be B. A is called the major radius, and B is called the minor radius. Technically, the line that A is a part of is called the major axis, and the line that B is a part of is called the minor axis. Well, in this case, the major axis that's horizontal, the minor axis that's vertical. But that means I want to make A bigger than B. If they're exactly equal, we have a circle. Only difference between that equation for a circle where I divided out the r's and the equation for an ellipse that I have different numbers on the bottom. And the bigger number tells me the bigger direction. A is bigger than B, so that means that the x direction is longer than the y direction is.
What if I want it the other way?
Switch the numbers. The major axis, the long axis of my ellipse, is horizontal in that case, because it's under the x term. If it's under the y term, then the major axis is vertical. So the equations for an ellipse are almost the same as the equations for a circle. We just have to differentiate the scaling, which way is the long way, which way is the short way. It turns out that if you want to draw an ellipse, what you need are those two numbers, A and B. And that defines a box. I just now made this equation up out of whole cloth. Where is the center of that ellipse? It is at 0, 0. I'm not subtracting anything from x or y. So h and k are both 0. To figure out where this ellipse lives, we find the intercepts. If I set y equal to 0, then I get x is 3 or negative 3. Those are the ends of the major axis. It's 6 units across. This one gives me the minor axis. I go 2 up and 2 down. Which means if I make a box with vertical sides going through the negative 3 and the 3, and horizontal sides going through the 2 and the minus 2, I have a box that my ellipse lives in. And the curve itself should be tangent to those 4 dots. But that really is going to be a very bad pain in the neck to draw, isn't it? So it turns out that the way you actually draw an ellipse is based on the geometry part that I skipped over. Remember, I talked about distances back when I talked about parabolas. Turns out there are 2 more points inside that box that are important, and they're called the foci. Like we had a focus for our parabola, we have 2 of them for the ellipse, 1 on each side. They'll be on your axis. By the way, these points those are called the vertices. And these points don't technically have names, but they're on the minor axis, right? So I'm going to call them the minor axis points. And notice the vertices go with A, the minor axis points go with B. And the foci go with C because that's in the word focus. Okay. It turns out that the geometry property I want is again related to things coming out of the focus. And it's drawn for me on page 676. An ellipse has the amazing property, geometrically, that the distances from the foci to any point on the curve is a constant. If you add these two distances going up to this point, that's the same as if you add the distances going down to that point. It's the same as if you add the distances going over to that point. It doesn't matter what point on the curve you have. This was actually proved by Johannes Kepler as part of his proofs that orbits are actually ellipses, not circles. And the sun, the center of the sun, is one of the foci. With a lot of work, and the algebra is actually down here and I'm not going to bother with it, with a lot of work, we can show that the equation to find C is almost Pythagoras. Almost, it's minus, not plus. So in this case, where are our foci? What is the value of C in this problem? Yeah.
We could square root of 3 squared minus 2 squared would be root 5.
Now the square root of 5 is 2 1/4. 2.24 something or other. Close enough to 2.25. So my foci are here. And if I were to take two thumbtacks and put them at those spots, and then take a piece of string the length of the major axis tied to those points, I could pull the string tight and draw the ellipse. I went down to the hardware store in Robinson Town Center. There's this Rockler woodworking store. And I was killing time, and they had an oval cutting jig that would cut perfect ellipses. This oval cutting jig, how much do you think it cost? $100. My oval cutting jig is 2 screws and a piece of string, damn it, it cost me a nickel. I saved $99.95. All I have to do is the right amount of math, know how big across and how big top to bottom, because if I have A and B, I can tell you exactly where to put the 2 screws, exactly how long the string should be. I love being able to do that cheap. Again, I then end up with an equation that looks like this all the time. If I'm going from left to right, what if I'm going top to bottom? And the bigger number is under the y term. Same 2 equations. What's not there is the way to find C. There's no mention of focus anywhere in this formula. So I need that. But it's almost Pythagoras, damn it. Now, I'm not the greatest artist, and I didn't bring my thumbtacks or my string, so I'm just going to approximate here. There's my ellipse. But since I know A and B and H and K for this problem, I could put them in here in this formula, in this first one, since that's the horizontally oriented one. A is 3, B is 2, H and K are both 0. There's my picture in the box that goes from -3 to 3 and -2 to 2. a hyperbola takes an ellipse and rips it inside out. So literally, you think of taking that picture and turning it to the outside of the box. So I'm going to take that same equation and to turn it around, I change the plus to a minus. That's the only difference between an ellipse and a hyperbola. Instead of adding, you subtract. And now I change which is A and which is B. A is always the one that goes with the positive fraction. So in this case, A is 9. I'm sorry, A squared is 9 and B squared is 4. But only because A is in the positive fraction, B is in the subtracted fraction. Which means I could just as easily do one that looked like this, and it would still be A and B, even if the fact that now they're not, one is bigger than the other. It's the one that's subtracted. Okay, wait a second. If I do this, in the ellipse, the curve wraps around the foci, right? In the parabola, it wraps around the focus. In the hyperbola, it should wrap around the focus also. But that means the focus needs to be outside the vertex rather than inside the vertex. Which means to find C, I need to make the number bigger, not smaller. So it actually does turn out to be Pythagoras. So my C this time is the square root of 13, which is 3.6 something, 3.5 something, bigger than 3. But again, I have this box. Right? And now I need to figure out how to draw this curve because it doesn't live inside the box anymore. It lives outside the box. And since it lives outside the box, what I need to do with this box is connect the corners. I want you to draw the diagonals on this rectangle. So I pull out my ruler and I draw diagonals. Now the vertices are in the same spot. The vertices are still on what we call the major axis. They're still here at 3 and minus 3. But there's no curve going up or down. The curve lives within these wedges. Those lines that we just drew, they're asymptotes. Which means we start here and we don't cross them. And there's my hyperbola. Question for you. The asymptote that goes up and to the right, the one where the word asymptote is, what's the slope of that line? Because we went up 2 and over 3. We get those right from here. Because they're symmetric. Now they go through the center. So in this case, it's 2/3 x. If we had an h and we had a k, we could move those around. Y minus h plus or minus 2/3 x minus k. But you always get the slope, y number, x number. If we were doing this one, the slope would be 3/2. Again, that's not in here, but it is on the formula sheet. Okay. Questions? Almost all of this should have been reviewed. That means we should try and start doing this stuff new. Which means looking at this in polar and parametric and other ways and doing calculus on them. And that is what we will do on Wednesday. You all have a wonderful rest of your day. I'll see you then. There are lots of very good examples in the text.